Alright, so in class I showed you guys how to use your calculator to basically plot your function and then use that function in the scratch pad to find your answers. Okay, so A was P of 20, so let's remember that we actually graphed the logistic function right there. Okay, so we graphed it in our calculator, and then you can go back to your scratch pad and use f of, because we graphed it in f of 1, so we can use the var button and then use f of 1 because that's what we want to do, and then we plugged in 120 and we got our answer. That's for part A. What is the predicted population of Alaska in 2020? Part B says how fast, which means that we actually have to use the derivative. So again, we're going to use the calculator, and we went to calculus, we went to numerical derivative at a point. Our function in our graph was in terms of x and y, so that's why our variable is going to be x. Okay, we're not going to worry about p and t like it says in the problem. And we solved for 20. And then in here, we're going to take the derivative of what? Of the function that we graphed, which was, again, you take vars, and it was f1, and you have to put x because you have to give it the correct variable term. And that's how many, that's our rate. So how fast was the population of Alaska changing in 1920? It was changing at about 1,678.08 people per year. Okay, it didn't say it around or anything, so I'm going to take the full decimal. And then you can do this for 1940, which is P prime of 40 years, and P prime of for 1999, which is 99 years, and figure out the rates. Use your calculator. Alright, part C says, when was Alaska growing the fastest? And what was the population then? So remember, whenever they're asking this about the logistic growth, so if this is our logistic function of Alaska's population, remember our carrying capacity was 895,598. That was L. At what point was it growing the fastest? That means at what point was the slope, the derivative, the steepest? It's at L divided by 2. So for C, when was Alaska growing the fastest? It's growing the fastest at half the carrying capacity, because that is when P prime is the steepest. Okay, that's when the slope is the steepest. So how would we write this down? So population is growing the fastest when P of t is equal to 895,598 divided by 2. Okay, you divide those and you get 447,799. So what if we wanted to figure out, so basically when was Alaska growing the fastest? It's growing the fastest when P of t is equal to this many people. And what was oh, sorry. This is when it was this many people. The question is when. So t equals what? So I need to solve for t. Now I'm going to use my calculator because I need to figure out what this is. Okay? So here what we can do is go back to the graph, and we want to find where this function is growing the fastest. We already figured out that it's when P of t is equal to 2, so I can actually graph that as f of 2. I can do 598 divided by 2. Graph that. So at this point right there, the graph is growing the fastest. And how do we find out what this point is? We find the intersection. So we analyze the graph, find the intersection, lower bound, right? We sandwich in that intersection, and there it is. It's growing the fastest at 82.8 years. $82.8. Okay, so basically 1982.8 years. So what is that? Like maybe September. Okay, so in September of 1982, it was growing the fastest. All right, and then the second part, and what was the population then? Oh, it's right here. 447,799 people. Okay. At t equals 82.8. All right, part D. What information does the equation tell us about the population of Alaska in the long run? Like all logistic growth functions, it tells us that the limit as t approaches infinity of p of t is going to be our carrying capacity, which in this case, it's 895,598 people. Okay. All right, just going back to this question right here, our population was at 82.8 years. It is 447,799 people. But if we were to ask how fast was this growing at that point? Okay, so the question is the rate, what was the rate at exactly 82.8 years? Do you guys know how to figure that out? So how fast was it going? It doesn't ask that, but it could. So how fast was it growing? You would plug this into your calculator and you would get that during that peak growth, there were 11,553.2 people per year being born, okay, at 82.8 years. Okay, moving on to the next question. So the AP exam loves to ask questions that require you to recognize the parameters of a logistic growth problem for either the equation or the differential equation written in different formats. So this requires you to manipulate the equation to fit one of the two standards. Here are our two standards. This is the differential equation, and this is the logistic growth equation. And let's look at the problem that is given to us. Okay, remember that this is something that you do have to memorize. All right, the growth rate of the population P of bears in a newly established wildlife preserve is modeled by the differential equation dp dt is equal to 0.008 p times 100 minus p, where t is measured in years. So, which one of these two does this problem look like? They are actually not giving us the differential, the logistic growth. They're not giving us the equation, they're giving us the differential equation. But what this tells us is that this right here is my K, this is my Y, this is my L, because it looks exactly the same, okay? And this is my Y. So what is the carrying capacity for bears in this wildlife preserve? It's right there, 100 bears. Now its second part, part B, says, what is the bear population when the population is growing the fastest? So when is it growing the fastest? It's growing the fastest at half the carrying capacity. So what is the population? It's 100 divided by 2. So the population is 50 bears. So during the moment of peak population, you have 50 bears. Part C, what is the rate of change of population when it's growing the fastest? So rate of change is basically the derivative, right? So it's P prime. What is the rate of change of the population when it's growing the fastest? So it's P prime of 50 is equal to what? That's what it's asking. And keep in mind that they actually gave us the differential equation. So they gave us the derivative equation. So really, we just have to use this equation, dp dt, and let p equal 50. Sorry, p of what is 50? That's what they were asking here. Okay, what is the rate of change of the population when it's growing the fastest? So P prime, nope, I was right. P prime of 50 is what? So all we have to do is really plug 50 into the derivative equation. Okay, so it's 0.008 times 50, 100 minus 50, do the math, and you end up with 20 bears. Oh, per year, sorry, because it is the rate of change. So it's 20 bears per year. So at the moment when the population is growing the fastest, it's actually growing at a rate of 20 bears per year. So what this is telling us is that right here, the slope of this tangent line is 20 bears per year. All right, the next question looks harder than it really is. Suppose that the population develops according to the logistic differential equation, dp equals 0.2p minus 0.002p squared. So they tell you that this is a logistic differential equation. Okay, now keep in mind that this right here, does it look like our form that we like to see, that we are able to identify the carrying capacity, the k, and the y? It does not. Our form, so this is not in our format that we'd like to see. We don't know k, we don't know p, we don't know l, we don't really know much of anything here. So what we want to do is we want to rewrite this in that form. Now I haven't even looked at the questions yet, okay, but we do want to rewrite it so that we are able to answer these questions. Now look at this first question. If p of 0 equals 5, what is the limit as t approaches infinity of p of t? So really, all of these are asking the same thing. What is the limit as t approaches infinity? The question is what is L? What is L? What is L? They're all going to be the same exact answer because it's the same exact function. So this furthers the idea that we do have to extract this. We have to basically rewrite this in the form that we know, which is dp dt is equal to kp times L minus P. Now I just changed P, Y to P just because that's what we're dealing with, okay? Now look at this equation, and look at this equation, and what do you notice? This is a quadratic, and this is a quadratic that has been factored, okay? So basically we want to factor out a P, okay? So we want to factor out a P. So dP dt is equal to P. And we want to factor out a number here that will keep the second part P by itself. So that way I can solve for whatever my L is. So the only way I can keep P here by itself to make it look like this format is if I factor out a 0.002. Because if I divide both of these by 0.002, then what am I left with? Over here you're left with, if you factored out a 0.002p from this, you're left with 100. And here you factor out a 0.002p from this, you're left with just p. And I just did the work for myself. So there's not much else to do, because now what is my carrying capacity? So L is my carrying capacity. And I really didn't have to do much work because I just put it into that format. So here, to answer these questions, it doesn't matter what my y-intercept is. It doesn't matter where my population is. Based on this function, as the limit approaches infinity, as t approaches infinity, L is 100 for all of these. Okay? Now, part D, sketch the solution curves for A, B, and C. Which one has the inflection point? So part A says that this is all logistic model, so keep that in mind. And then part A says my y-intercept is 0.5. Let's call that 0.5. My L is at 100. So I'm going to draw that right here. Basically, I know that if this starts here, it's going to start growing exponentially, and then it's going to taper off as t approaches infinity. Part B, it's still the same carrying capacity. Okay, 100. So y equals 100, or L equals 100. But here my y-intercept is 0.60, so I'm actually closer to the carrying capacity. So that means I'm not going to really have a very massive amount of a big, how should I say this? It's not really going to be, exponentially growing and then it's getting closer, because keep in mind that if 100 is here, where is my L divided by 2 going to be? It's going to be at 50. So at 50 is going to be the inflection point. That's the point where my graph is going to flip from concave up to concave down. So here, if I'm starting at 60, and at 50 is the point where it kind of switched, right? Then that means the rest of this curve is kind of doing one of these. It's just going up. It's all concave down. Okay? Which brings us to part C. My carrying capacity is still here. My greatest increase is still at 50. But my y-intercept is at 120. So if the function is actually approaching 100, then basically this graph just has to show that it's approaching 100 from the top. Okay? So which one has the inflection point? Which one actually has a change from concave up to concave down? It's this one. This does not have an inflection point because the inflection point is below the y-intercept. So we're not even graphing it. Alright, the last problem. And then tomorrow I'm going to have a worksheet for you guys to do more of these, okay? The rate at which the flu spreads through a community is modeled by the logistic differential equation. So it tells us that this is a logistic differential equation, and it's actually in the format we love. So it's the format we prefer, which is dp dt equals kp L minus p, where t is measured in days, and of course you can't have negative days, so t has to be greater than or equal to 0. Okay? So if p of 0 equals 50, solve for p as the function of t. So think back, what is this actually telling us to do? What do we want to solve for? We want to solve for p as a function of t. So what is this problem asking us to do? We want to find the particular solution. Now, if we didn't have the Lice minus Licht equation, this would take a lot of work, right? But here we want to find the particular solution for dp dt when p of 0 is 50. But remember, the last video we actually spent 20 minutes finding the general solution. So we already know the general solution of the logistic function in this form. What is our general solution? It's p of t equals Lice minus Licht. And for this particular problem, we actually know that L, what's our carrying capacity, is 3,000. 1 plus C E minus 3,000. K, what's our K? It's right there. 0.001 T. So that is our general solution. But now we want to find the particular solution when p of 0 is 50. So that means t is 0 and p of t is 50. So 50 equals 3,000. 1 plus CE negative 3,000 times 0.001 times 0. Let's solve this. So 50 equals 3,000 over 1 plus CE to the 0. What is CE to the 0? 3,000 over 1 plus C, because e to the 0 is 1. So now we want to solve this, where we multiply both sides by 1 plus C to cancel out one plus C. Now we're left with 50 plus 50C. I don't know why I just did that. Just made things complicated, but it's okay because it still works. I could have just divided by 50 and then subtracted 1. But whatever. We can subtract by 50 and then divide. So subtract 50. 50C equals 3,000, 2,950. Divide by 50. So you get C equals 59. Make sure I did this correctly. Yes. So if C equals 59, that means my particular solution is P of T equals 3,000 over 1 plus 59e to the, I'm just going to simplify this part to negative 3,000, sorry, to negative 3t. And that is my solution for part A. All right, part B. Use your solution in part A to find the size of the population in 2 days. So basically P of 2 is what? You guys can figure this out. And part C says, use your solution to A to find the number of days that have occurred when the flu is spreading the fastest. So when is the flu spreading the fastest? Let's look at this part. Remember, if this is L, the flu is spreading the fastest at L divided by 2, which is 1,500. So the question is, when P of T is equal to 1,500, what is when P of T is equal to 1,500, T is what? So I'll let you guys take the lead on this because we're getting close to 30 minutes and we'll double check tomorrow. Enjoy.